Okay, so today's lesson is over 10-1. We are going to learn about a chi-squared distribution. So the table that we're going to be using is on the very back of your packet, table number 6 that we haven't used yet. So keep that guy handy. All right, so this is sometimes called a goodness of fit test, because we use it to determine if our data fits a certain distribution that's expected. It could be a symmetric distribution, it could be a right tail or left tail or symmetric distribution. It just depends. We've seen binomial experiments before where there are 2 categories only, where it was just success or failure and that was it. Now we're going to be using what's called a multinomial experiment, where we have more than one or more than 2 categories that we're going to be using. But our probabilities remain the same throughout. The probability of each outcome is fixed, and each outcome is classified into those categories. We're going to be using K in a minute to figure out how many categories we have. All right, so let's see here. It says to calculate a test statistic for a chi-square goodness of fit test, you can use observed and expected frequencies. Observed frequencies are what actually happen. So survey results or data that's collected from an experiment. Expected frequencies are calculated things. They're theoretical based on probabilities that are expected to happen, okay? So you're going to see a lot of O's and E's when we do this section. So O's are going to be values that are given to us, nothing we have to calculate. E's are going to be values that we have to calculate. What you need to know from that little bit at the bottom here, E represents expected frequency. N is the number of trials, or it could be the sample size, so that depends if it's an experiment or like a survey. And then P sub I is going to be the assumed probability for each category I, whatever that happens to be. So pretty much to calculate an expected probability, you're going to multiply N, the number in our sample size, times the expected probability, so it's going to be a percent or a decimal, and then we're going to get the number of items that are expected to happen in that category out of the total in theory. Okay, so you should have this chart on your paper, I believe, right? It's on there? Yeah, okay. So it says the tax preparation company randomly selects 300 adults and asks them how they prepare their taxes. The results are shown at the right. Find the observed frequency and the expected frequency using the distribution on the bottom there for each tax preparation method. Okay, so what you see at the top here are survey results. So they are the observed frequencies. There's nothing that we have to calculate. Okay. We're going to use the percentages that are expected to happen to get our expected frequencies. Okay, so these are all of our O's we would use. To get all of our E's for each respective category, we're going to take the percent that we're expected to get for accountants by hand, computer software, however people do their taxes, and multiply it by N, the number of people that were in this survey, which in this problem was 300. So we're just going to do 0.24 times 300, which is 72. So that's saying if we expect about 24% of people to say that their taxes are done by an accountant, that would relate to if 300 people are surveyed, we should expect 72 of them would answer in that way. Okay, and then we just multiply all of the other categories by 300 as well to get those expected frequencies. So 0.2 times 300 gives me 60. 0.35 times 300 gives me 105. 0.06 times 300 gives me 18. 0.15 times 300 gives me 45. If you want to check that your expected frequencies are correct, what do you think the sum of them is going to equal at the end? It's going to equal our N, 300, so that's how we can check it. Okay, as long as all of our percentages added up to 100, we should expect that that column is going to add up to 300 as well. All right, questions getting expected frequencies? Pretty quick little calculations. Okay, the next slide on your paper is yours to try. We've got some survey results here. Calculate the expected frequency for each type of response seen in the pie chart. I'll give you a minute and then we'll check our answers. Correct answers. These are quick. Are as follows.
So they can't have like a decimal place?
Right, so if this was an actual survey, we wouldn't have 0.5 people answering a certain way. So this is just in theory though, remember? So this isn't going to actually happen, so we're going to keep that decimal there. And we're not going to round. If we needed to round, 3 decimal places would be appropriate. You're going to see in a minute, we're going to have some big tables, and we're going to use this value a few times in the table. So although in reality, we want a whole number there, if I rounded that, my chi-square value is going to be off by quite a bit in the end. So because it's in theory, we just leave the decimal. Okay. Other questions on that? All right, so on the back of your paper now, let's get to that hypothesis test we want to do. Okay, so remember, we're trying to figure out if a given set of data matches a certain distribution. That's going to be our claim. When you write a hypothesis test, the null and the alternative are always going to be the same, and for these, we're only going to write it in words. We're not going to be writing it with symbols and words like we've done in the past with like the mean equal to or the proportion greater than or equal to, that sort of thing. When you're doing these, the null hypothesis will always be that our distribution fits an expected distribution. So it might see our distribution is uniform, or our distribution is 20% this category, 10% this category, 30% this category, whatever the claim is. And then the alternative is always going to be the opposite of that. So the alternative is always going to state that the frequency distribution does not fit the expected distribution of being uniform or whatever, okay? So for example, we just did a tax problem a minute ago where there were different categories and there were percentages of people that answered that they use an accountant or computer software or whatever to do their taxes. This is what a null or alternative hypothesis would look like. The null is that the expected distribution of tax preparation methods is 24% by an accountant, 20% by hand, 35% computer software, so on and so forth, and that was the claim that was being made that we would test. The alternative hypothesis is that it is different from the expected distribution, and that's really all you have to say. It's not what's written in the claim. Okay? All right, so here are the steps to a chi-square distribution. A picture of a chi-square distribution was on the first slide that I had. It's also at the top of your purple paper there on the back. It always is going to look like this. So we've got that long tail on the right side. So it is always going to be a right tail test when we do these. You don't have to worry about, is it left tail, is it right tail, is it two tail, what's that going to do to my significance level? It's always a right tail test for these problems. First thing we have to do is verify that each of those expected distributions that we just practiced calculating is at least 5. So that's kind of our category that we make sure that we meet those expectations to be able to do the hypothesis test. If each expected distribution is not greater than or equal to 5, then you just say we can't do the hypothesis test. Then we identify the claim, the null, and the alternative hypothesis, like we saw on the previous page. Level of significance will likely be given to you. Degrees of freedom, instead of an N, it's a K here. Remember, K is going to represent the number of categories, but it's still 1 less than that. We're going to find a critical value from our chi-square chart. Then we're going to do the test statistics. So this is the formula that we're going to want to be using. And I told you there's going to be a lot of O's and E's. So remember, O is the observed frequency of a specific category. E is the expected frequency of that specific category. So we're going to see some columns when we do this again. We're kind of doing this in phases like you did with like your standard deviation before. So we're going to do O and E, then we're going to do O minus E, then we're going to do O minus E squared, then we're going to do O minus E squared divided by E. And then that last column again, that summation symbol tells me to add all of that up. And that's going to be our chi-square value that then we're going to compare to our value that we see in our chart. And we're using rejection regions. If our value is in the rejection region, we reject, and we say there is enough evidence to reject or support whatever our claim was. If there's not enough evidence, we are failing to reject. Okay, so we're just going to do 2 problems, And these are what your worksheet is going to look like that you guys are going to do tomorrow. All right, a researcher claims that the number of different colored candies in bags of dark chocolate M&Ms is uniformly distributed. To test this claim, you randomly select a bag that contains 500 dark chocolate M&Ms. The results are shown in the table below. At a level of significance of 0.1, test the researcher's claim. All right, so we are going to start by writing a null and an alternative hypothesis. Okay, so the null hypothesis is that our frequency distribution, or the distribution of dark chocolate M&Ms, matches what is being claimed. And the claim is that it's uniform. So the distribution of M&M colors is uniform, which means there's the same amount of each color. And then the alternative hypothesis is the opposite of that. The distribution of M&Ms is not uniformly distributed. Okay. And then our claim is the null here. They're claiming that it is uniformly distributed. Okay. So what we have on our chart, we have frequencies of some bags of M&Ms that they opened. So those are our O's. They gave us our O's, the observed frequency of each. The E's here, we don't have, and we have to calculate. Now, the ones that we did in class so far, we had a percent of each. Uniformly distributed means if I have a bag of 500 M&Ms, and how many categories of colors do I have? That's going to be our K. How many colors are there? 6. Each frequency that's expected is 500 times a sixth, or divided by 6. So you can do that real quick. 500 times 1/6, or 500 divided by 6. And we're going to get the same number for all of these. And I'm going to give it 3 decimal places. 83.333. 83.333. All the way down. So that's what it would look like if it's uniformly distributed. All of those values are the same. 83.333. Okay, now it's up to you if you want to do 3 more columns, or if you're feeling confident, you can go straight to this guy. O minus E squared over E is the column that we're looking for. Okay, so now to get to that, if you wanted to do separate columns, we would have to do O minus E, get a value. O minus E squared, get a value. And then divide by E and get a value. I don't love doing all those columns because it's like a lot of rounding and writing, and I could just do it all on my calculator anyway. And we have our graphing calculators, so we might as well use them. So if you want to try the first one real quick, just be careful with your decimals and be careful with your parentheses. You would do 80 minus 83.333, square that, and then divide by 83.333. And again, I'm going to give everything 3 decimal places. You should get 0.133 if you do that right. Okay, and then we just do it 5 more times for each category. So 95 minus that. You can really just go back and change numbers if you want for each of these, if you've got your fractions set up. 1.633. 0.261. 0.001. 0.645. 0.341. Okay. All good with those? That's crazy. All right. We're going to sum them up. And this sum is our chi-squared test statistic that then we're going to make a rejection region and see if it's in that rejection region or not to make our decision. All right, so 0.133 plus 1.633 plus 261 plus 001 645 plus 0.341. I get 3.014. Okay, so now to get our rejection region, our chi-squared shape is going to look something like this. It's going to have a tail on the right. It's a little rounder than usual, but it's fine. And then we're going to look at our chart to find where that rejection region starts. So it's always going to be on the right tail. That's fine for like a rough sketch there. Our level of significance here was a 0.1. So we're using that. Our degrees of freedom is always k minus 1. And k here we said was 6. So 6 minus 1 is 5. So that's how we know what to look for on our chart. So we're going to find 5 on the side. We're going to go over to 0.1. And we get a critical value. And they're going to use a sub O. If you look at a textbook, that's what it's going to represent with this. 9.236 is where that rejection region begins, and then it goes to the right. So is our value in that rejection region? It is not. So do we reject or not reject? We fail to reject is our decision, and then we summarize the same as before. We say there is not, in this case, enough evidence to, and then my claim was the null, so reject the claim of uniform distribution of colors. So we're saying we don't have enough evidence to say that's false. If you look at all of those observed frequencies, they're pretty close to each other. We don't have one category that's a 50 and the other category that's 120, and then we make them a little further off. So we test the full distribution with this and say, they're close enough, so we don't have enough to say it's false. Any questions on that? All right, the last problem of the day, and then we won't do anything until tomorrow. We'll get the worksheet in class, and you can do a couple of these for practice. Why don't you guys try this one on your own? I'll give you, I don't know, 5-10 minutes, and we'll put the answer up, and that'll be it. Okay. All right, whenever you're ready, here are your answers. So here the claim that was being made was that it was different than 10 years ago. So the null is always still that the distribution matches what we have. So the distribution is the same as 10 years ago. And then this time, the fact that the distribution is different being the alternative hypothesis means that the claim. We have all the O's again. The observed frequencies are our survey results. The E's are just like we practiced at the beginning of the lesson, where you take your N value, which 400 people were surveyed, multiply it by the percent that's expected, and then you can see that that column totals up to your N value, or 400. Then each O minus E divided by E, I didn't have to round as much on this one. I got 6.691 for my chi-squared test statistic, using a level of significance of 0.05. There's 8 categories, so degrees of freedom is 7. My chi-squared value, I have a C there for critical value, but again, your book's going to use an O at the bottom, is 14.067. So again, ours is not in the rejection region. So we do not reject the null, and we say there is not enough evidence to this time support the claim, because the claim was that alternative hypothesis. I'll leave that up there for a few minutes if you need to correct anything. So that's all we're going to do today. I'm not even going to give you the worksheet today. You guys have 20 minutes now. You can use it as a study hall. Get ready for other stuff for exams if you need to. Tomorrow, all we're going to do are 2 problems like this on a worksheet. You're going to turn it in. You're going to get 10 points for a homework assignment for that. And that's it. And then we'll move on. We're just going to do a little bit each day. Okay? Nothing outside of class. Questions for me? All right. Good deal.